All right, can everybody hear me? I had a vested interest to stay on track because I'm moderating my own session. And that's what I'm now going to do. But I'm really only the warming up for Ken Edgecombe, who's going to talk about this thing in the real world. So I'm going to keep it short. And Ben Daman is going to really keep me really sharp. So, okay, there we go. I would like to spend a few minutes talking about our latest and greatest product in the CMT space, the internally called Victoria Falls processor. I'll focus on the architectural aspects of that design. Okay. The official product name is UltraSPARC T2 Plus. Occasionally I may call it Victoria Falls, but it's all the same. So I'll go over the architecture fairly briefly, then I'll talk a little bit about the systems that we have, including the system that Ken has, and I'll say a few words about what we're doing in Solaris and have done in Solaris to make it scale to these kind of fairly novel kind of systems. So I'll start with the goal. What we wanted, we had Niagara 1, or UltraSPARC T1, then we had T2, and what we really wanted was to go beyond that single socket, but maintain a shared memory system. That's really what we wanted. So what we did, and that was already pretty much from the design when we did T2, we wanted to make it scale to bigger systems in a shared memory way. So what we currently have is we have two-way systems. The processor is designed to go to four-way. Roland already mentioned it on his roadmap slide. That is NDA information, but that's the Batoka system that will be four-way. And here's a little floor plan. That's just for the fun of it, just to show you. You can see in the center, literally in the center, there's the crossbar, pretty much connecting all of the components in the system. You can, in red, you'll see the 8 cores, and each core has 8 threads. That's a single T2. The major change when we did the T2 Plus, which is kind of not immediately visible here, is that we added cache coherence. And because of the cache coherence, we can go outside of that chip and still maintain a single system image. That's really what we did. Okay. So I would say the heart of this design, the novel thing in this design, is to do the cache coherence. And for that, what we did, we reduced the number of memory control units from 4 to 2, and we use those two to implement the cache coherence. That's really what we do. We can use the same interconnect, so that's good. And we introduced 4 coherence planes across the system to maintain that kind of coherence. Okay. So this is a very kind of crowded slide. This is the high-level block diagram of the system. You'll see the 8 cores there, C0 to C7. As you know, on the T2 and the T2 Plus, each core has its own fully fledged floating point unit. That was a big change compared to T1. Then on top of that block there, we have the L2 caches and the MCU, the memory control units. What's new is this CU. That's the coherence unit. And again, cache coherent allows you to have a single system image, even if you're spanning multiple processors or sockets. And what we have on the coherence side, we have 4 links. Each link has 6.4 gigabytes per direction. It's bidirectional, so you have 12.8 gigabyte per second bandwidth, coherence bandwidth per link, and then there's 4 of those. So in total, this system has a little over 50 gigabytes a second for coherence traffic. Quite a lot. Okay. The other details are there. I assume you're at least somewhat familiar with UltraSPARC T2. 8 cores running at 1.2 gigahertz or 1.4. There's 64 threads per socket. So the 2-socket system has 128 threads, again, in a shared memory environment. So that's really what I'm trying to highlight here, the coherence part, because that's the novelty on this chip. Oh boy, this is not the way it should look like. It's not like one of our architects had a bad day and just drew arbitrary lines. It's it's my presentation program messing up. So those diagonals should not be there. I thought I had kind of gotten rid of them, but life is full of surprises. The reason that I put these in, so just to kind of ignore those weird lines, it's not really like that the architect kind of got berserk, it's the presentation program. The reason I put in this slide is to stress that the pipelines, the core is the same. So there were no changes at that level. So you got 2 units, each unit is feeding 4 threads. That's really, and that's how you get to the number of 8. And then there's the floating point unit. But the reason I put in this slide is I want to stress that the pipelines and everything is the same at that level. Here's a bit of a marketing view of the same thing. And with this technology, we can now go to more sockets. And again, this is a simplified picture, but describing a 2-way system, 16 cores, 128 threads, again, in a shared memory environment. So what that means is that any thread can get to any portion of the memory whenever it wants to, wherever the data is. This is for the techies. I just put it in for that. This is essentially saying the same. This is more detail on the cache coherence, and you can see what we call a plane, a coherence plane. And again, there are 4 of those. For those of you into cache coherence, it's maybe interesting to know that we have a MOSI protocol implemented there. And of course, we do cache-to-cache transfers, the C2C transfers. On the memory side, you can talk, even though it's only a 2-way system, it means that it is a CC-NUMA system. But it's a good CC-NUMA system. So you talk about local memory that is on your processor or accessible by your processor, and then there's remote memory that's on the other side and in the other processor, but you can still get to it. And this slide gives you some data. The bandwidth for reads is 21 gigabytes a second. The bandwidth for the writes is 10. In total, that gives us system-wide a little over 60 gigabytes a second bandwidth across the system. To me, the most interesting number is the remote penalty. So when you have a local memory access on your socket, that's about 150 nanoseconds that'll take you to get to your data. Then when you go remote, it'll take longer, and it'll take about 75 nanoseconds longer. So you're talking about an access time of about 225 nanoseconds. As I said, being more like a software guy myself, that's a really good number, but as a software person, you can't ignore it either. So this will mean that you have to do similar things as we've been doing on CC-NUMA architectures for a while. And I think Ken will say something about that as well. Then the products, we have 2 products. The physically smaller one, where you do have 2 sockets, so you can go up to 16 cores, 128 threads. You can go up to 64 gigabyte of memory on that, and a bunch of disks and I/O. The next model is just a scaled up version on the I/O and memory side, but on the CPU side, it's the same. It's either 1 or 2 sockets. So that's the 2 rack unit system. Again, up to 128 threads, but you get 32 memory slots, so you can go to 128 gigabyte of memory on this system, and you get more disks you can put in. So you're bigger on the I/O and disk side. I want to finish with a few words on the kind of things we are doing and have been doing in Solaris. This is a very heavily threaded architecture, and that's kind of amazing to me. We've been modifying and optimizing Solaris for a long, long time, and we're still finding things where we run into a scalability bottleneck. Of course, once we find them, we can fix them. So here's some things that we've been looking at. This is the summary slide. I'll show you a little more detail right now. So one thing that we found was Solaris performs what's called tick accounting, and that was a highly serial process in a way. It was a single-threaded activity. We never had a problem with that until we start doing these kind of systems. And anything serial on a heavily threaded architecture generally is not a good idea, especially not when it's in your operating system. So what we saw was the bottom line of this slide is as the system became unresponsive. You know, it got sluggish. And the way to solve it, which I can easily say because I didn't have to do it, is you multi-thread that part in the operating system. So now this tick accounting part has been multi-threaded in Solaris. It's available in update 4 or 5 of Solaris 10. In general, for those of you that want to buy these systems, I would try to go for the latest and greatest OS release that we have because we continue to put in these enhancements, if you can, of course. Okay. Another area where we saw issues were mutexes. And they'd really been optimized for the non-contended case. That means that you're the only one that cares about that piece of memory, and the other threads don't in time, overall. That was what our model was. Until, again, we started booting up these systems. So when you talk about a huge number of threads, this actually talks about 256 threads that I haven't talked about. That's for the future. So you're talking about a high number of threads. And what it came down to is that they're all trying to get to that same portion of memory, and again, you have a scalability bottleneck. And the first place where that showed up was in the network stack. That's where we saw it first. And again, we put in a different algorithm to make it more scalable. Then another thing is the CC NUMA side of this architecture, and in particular, the cost it takes to go remote and get your data. We've been working on that for quite a while. As hopefully many of you know, we have what was called memory placement optimization, MPO, in Solaris since Solaris 9, because we needed that on the big 25K type of systems. Today, you'll need it on Optron, and you'll need it on this kind of multi-socket Victoria Falls type of architecture. And essentially what Solaris will try to do, it'll try to get you the data local. And what's local is described in what's called a locality group or L group. So Solaris has a notion of what's close to me and what's further away. Okay, and that's what you do in Solaris. Now, I'm a little more involved in this kind of project, so I can tell you that we're working hard on making Solaris smarter and smarter to deal with these kind of architectures. You gotta throw overboard most of the things that you used to do in a Unix system. It just works the different way. Like the whole notion of uptime to look at the load is not really a good measure anymore. Okay. Maybe that's something for next talk. I got the almost a kill -9 signal, so I better speed up. We also optimize the network stack, and this is a fairly technical thing. We did what we call large segment offload, and in a way, what we're doing some sort of micro-parallelization in the low level of the network stack. That's really what we're doing. So again, we're taking advantage of the parallelism we have, and that just gives us fairly impressive improvements in single thread network performance, but also multi-threaded. We saw 20% performance improvement. Okay. And overall, the CPU time went down, so that was good too. Okay. So to conclude this very brief overview, again, I'm just warming you up for Ken. We have the two-way, and in the future there will be four-way servers that we haven't announced yet, but they're on their way to you. And in particular, we keep on tuning Solaris to give you the best performance for that kind of architecture. And with that, I want to thank you and give the stage to Ken. Thank you very much. And tomorrow I'll talk about the software, so stay tuned.
Ready to go? Okay, thank you. Well, thank you, and I guess I'm between everybody and refreshments.